Good afternoon to all of you. I, Dr. Nirav Y. Pandya, warmly welcome to all of you in today's webinar on behalf of whole Applied Science and Humanities Department of Padul University, Vadodara. I also warmly welcome to our today's speaker, Dr. Mitesh Joshi sir. First of all, I would like to introduce our today's speaker, Dr. Mitesh Joshi sir. Dr. Mitesh Joshi sir has completed his PhD in physics with a specialization of condensed matter theory from the Sardar Patel University, Vallabh Vidyanagar. Sir has total 16 years teaching experience at different institutes, which includes different science colleges, degree engineering colleges, and diploma colleges. Sir has also the around more than 10 years research experience, and as a part of that he has worked as a UGC project fellow at Department of Physics, SP University, Vallabh Vidyanagar, and also worked as a project scientist at IPR, means Institute for Plasma Research, Gandhinagar. Sir has published more than 24 research publications in various national and international reputed journals, and he has also participated in various seminars, workshops, STTPs, and trainings. Presently, he is working as a lecturer at Government Polytechnic for Girls at Surat, Gujarat. So once again, I warmly welcome to you, Mitesh Joshi sir, and I warmly invite you and request you to start the today's session. Thank you, sir.
Thank you, Nirav. Thank you, Kale sir. Thank you for the opportunity given me to present the webinar. Shall we start, sir?
Yes, sir.
Okay. So, the topic of today's webinar is basics of material characterization. Let me briefly conclude the, initiate the topics. There is two important things over here, material and characterization. So what is material? Let's first discuss what is material. Now, material in our sense, actually we are fascinated our day-to-day life by experiencing number of materials. So materials are everywhere. Even we cannot live without materials, you can say. So a material is a substance or objects which constitutes basically of particles. So they can be pure, impure, living, non-living matters, and may be classified in different categories like physical they can be classified in physical properties, they can be classified according to chemical properties like biological functions also. So you have a different types of material, and there is a particular science where you can study this kind of materials, its property and its applications. So material science is a study of materials and its applications. Now particularly material is made up of matters which is constituents of three phases: solid, liquid and gaseous. This also includes the plasma, which is a fourth state of matter, you can say. But broadly speaking about the condensed matter, where you have a macroscopic and microscopic physical properties of matter which is combined together. So here in condensed matter physics, we are particularly concerned about the number of material which are having the large number of constituent particles or systems. And it is extremely large when the interaction between the constituent particles are very strong. There may be different electromagnetic forces between the atoms, and by governing these forces may be governed by laws of quantum mechanics, electromagnetics, and statistics. So this comprises of all the basic branches of physics, like sciences like physics, chemistry, material sciences, and biosciences. So materials are everywhere, and we need to concentrate on that. So material history is very large. Here I have given a funny picture. Everybody knows this is evolution. In early life, early human life, it is said we are from ape and now we are moving from smart age. So all these ages which are defined starting from humankind has been named after the materials. Let's check out. So, as I said, each distinct age in development of humankind has been associated with the advances in material technology. And it is named according to that. Like first is the Stone Age. Like when human civilization started, there were materials like they found simple stones. They make it sharp, like they are processed. So you can say they are processing it. So the sharpness is a property, and they defined its applications. So like by using this sharp objects, they make caves and they live for centuries. But something missing here. So this is material science history, where you have a material, you process it, you define some properties, and you have some applications. So this has been going on since years and years. After the Stone Age, when they were digging, there was another materials which were available, like metals, called Bronze Age. In a Bronze Age, again, they have different materials, like different metals, copper, tin, alloys, and by processing it, they make it harder, sharper, and they define their applications, like arrow, bones, and everything. So these were around 1000 years back. After the Bronze Age, there was Iron Age, like we have 100 years back. Again, the same principle applies here. They have material, iron. They make it different processes like quenching, hardening, tempering, recrystallization, and everything. They make different properties of a material, like some materials may be very weak, some may be strong, ductile or brittle, or some may be easy to form. And according to that, they define different applications. So this is generally material science civilization going on since centuries. What is missing over here is microstructure. So after the knowing of this microstructure, this Iron Age will turn out to be Information Age. This is, as we know, we are living in this information technology age, where we are surrounded by semiconductors and all those electronic gadgets made by semiconductor chips. So what they have done, again the same principle applies over here. You have a material, silicon and germanium or carbon. They process it by doping some amount of material, by deposition, by growing their crystals, by oxidization process. They define their properties, like some materials may be insulator, some may be semiconductor, metal, semi-metals. And according to that, you have different applications, like we are using that computer, iPod, and everything from scratch to sensors. So when this happens, by knowing the microstructure of the material. So this is important aspect, microstructure of material. When they know this microstructure, there is a huge difference between earlier and human civilization nowadays. We are also living in another age, which is called nanomaterial age. Again, same principle applies here, from material to applications, but here now the size dependent properties is included, which actually leads us to a unique applications of the material. So I have given you the clue how to study material. You have a material, you process it. There may be some property, there may be some applications, but what you need to do is you need to find out the microstructure. So this is the traditional three mainstream material sciences from last 5,000 years going on. But the important thing here is microstructure. So how you can study the microstructure, that is important. So this is the basic principle of material science, where it is divided into three parts. Actually say two parts: materials and material processing, properties, applications, and microstructures. So microstructures means you can see up to micron size or below micron size. So I have given you some rough idea what about the micron size. So let's say you have a soccer ball which is the size of around 20 centimeters or more. Then you have a pit flyer that is around 1 millimeter size. Our hair, which is of 80 micron meter size. Our blood cell, around 7 micron size. Virus, we are familiar with nowadays, is having 150 nanometer size. The smaller size, again, we have to be very precise over these things. So titanium dioxide particles, which are coated on some materials to make it other properties of the material, which is around 30 nanometers. I'm going still nano size materials. So a logo on IBM chip, 5 nanometers. DNA, our body DNA structures, it is of 2 nanometer sizes. Carbon nanotube around 1.4 nanometer sizes, and carbon bulky ball, you can say, around 0.7 nanometer size. So we have to study all this material for their properties and applications. So can we see up to that limit? No, we cannot see it. We cannot see that because our eyes are having some range. Our visible eyes range are from 380 nanometers to 780 nanometers. So that is fall in visible range. You can say with your. So below that range we cannot see it. Above that range also we cannot see that. So the size of the material below our normal eyes we cannot see has to be done by means of some other things. You can use the ultraviolet, you can use the X-rays, you can use the gamma rays, but it has some difficulties. So what has to be done? So it has to be something, there has to be some probe which we can use to get the magnification of micron size or lower size. Like you have up to this dust particle, you can see bacteria, viruses, atoms, and the part of atoms that we cannot see by using that spectrum. So this is general view of material science. Now to study this, we need some science. This is called material characterization. Now, what is characterization? So, characterization is nothing but the identification of something. Now, characterization may be of two kinds: microstructure and macrostructure. Macrostructure is just by looking at some material, you can identify this is square, this is sphere, this is cylindrical. But in a microstructure, you need to go inside the material and identify it. So basically, material characterization is of three kinds: microscopic, spectroscopic, and diffraction type. In a microscopic, you can use the optical microscope, electron microscope, or other scanning probe to get the image of materials. In a spectroscopy, you are allowing the material to reflect or absorb the some amount of light in different forms. Like in some cases, you can use X-rays called energy dispersive analysis of X-rays. You can use electrons. So energy loss electrons are there. So it is called EELS. XPS, X-ray photospectroscopy, Auger electron spectroscopy, and and some small ion microscopy is also there. So this is just a spectroscopy. Spectroscopies are also used in chemistry, where you can use the ultraviolet and visible and IR spectra. So they are also a part of spectroscopy. Diffraction, again, I can say diffraction is to be done by using the X-rays, electrons, and neutrons. They all have a different properties. They all behave as a wave, and they all give you different information, and they are used for different purposes. So this is general material characterization. So as I said, material characterization is of two kinds: physical characterization and chemical characterization. In a physical characterization, you need to identify the material physically. Obviously, in a chemical characterization, you need to identify what is present inside the material, like what chemical element is present, what chemical groups are present, what type of bonding will be there, what will be the thermal temperature, what will be the other chemical properties of the material. That can be done in chemistry. So that is also material characterization. So general material characterization is defined in basically these two categories: microscopy, spectroscopy, and diffraction. This is for physical characterization. Now, all these things we have to prepare. For all these things, we have to prepare the sample. You can prepare the sample by mechanical grinding, chemical polishing, ion bombarding, crushing, and there are multiple sample preparation methods used for different spectroscopy, microscopy, or diffraction conditions. Here, particularly, I am today just taking about the scanning electron microscopy. As I said, the visible light, it is also used called optical microscopy, X-ray. So when X-rays are used as a probe, you call it as X-ray diffraction. There are two types of X-ray diffraction: X-ray photoelectron spectroscopy, neutron. Again, neutron diffraction is called. Ions. When ions are used, it is called secondary ion mass spectroscopy. Electrons, you have a number of electron microscopy called scanning electron microscopy, transmission electron microscopy, holography, diffraction, electron energy loss, and electron dispersive analysis of X-rays, Auger electrons. So they have different names according to what probe you are using. That means on a sample, what kind of probe you are using to eliminate or to identify the structure. These are the simple microscope. Let me give you the microscope, the information regarding the microscope. So we are already aware of this optical microscope. These are the optical microscope with the compound lenses, which are mainly used to magnify the image size. These are used in general microbiology labs, having the magnification power of around 10,000. 10,000, say 10,000x, you can say x is a number of, x is the original things, and 10,000 times magnification will be there. This is electron microscope. So let's concentrate on electron microscope. Now, electron microscope has also a history. So in 1933, this first microscope was produced by Ruskin in 1933. taken the picture from Wikipedia. So this is a basic comparison of optical microscope, transmission electron microscope, and scanning electron microscope. One can easily identify that in an optical microscope, generally we are using the light source. Then you have a condenser, which actually concentrates the light on some specimen, and you have the eyepiece. So by objective and combination of objective and eyepiece, you get the magnification of the image. In comparison to the optical microscope, electron microscope uses the source of electrons. By using the magnification lens, we are projecting the electrons on the specimen, and by focusing the what is the interaction of the electrons with the specimen, you can have the two types of electron microscope. If the electron transmit to the material, it is called transmission electron microscope. And if you have the scanning type, then you have the when the electron interacts with the sample, and there are different phenomena occurred with the while interacting the electrons with the specimen, and you have a different kind of detectors around the sample. So you have a different kind of scanning electron microscope, which is also attached with the in the chamber surrounding the materials. You can say a material chamber, I can say. This is general you can say scanning electron microscope, which are now used in general material science labs. There are compact size also available nowadays. Depends on what magnification power you are required. So this is a sample chamber, I can say. And this is a column. Now, why you need a column? So let me give you some brief about the scanning electron microscope. This is generally the comparison of what you can see in a simple optical microscope, and this is just you can see in a scanning electron microscope. So here you can see the same picture by large depth of field and having a high resolution. The size of the object was around 25 micron size. Now, what is the basic physics? As I said, you cannot use the optical microscope beyond the particular limit. So the basic simple equations of physics gives you the advantage. Just I can briefly elaborate this. So you have the energy, which is in the form of photons. So E is equal to hf, you can say. H is a Planck constant and f is a frequency. By knowing the velocity of wave, V is equal to f lambda. So we can have f is equal to c by lambda. C is a velocity of light. It's a constant. So if I can put this in an energy equation, we have hc by lambda. Now the electrons are given the potential called kinetic energy. So kinetic energy is equal to the hc by lambda, which is equals to the half mv square is equal to hc by lambda. So we have the value of wavelength, which is in a form of velocity. So if I give the velocity in terms of voltage, I can write half mv square is equal to ev. So from this I can find out the velocity in terms of potential. You have the another equation, de Broglie wavelength equation, where you have a lambda is equal to h upon p. P is a momentum, so lambda is equal to h upon mv. By clubbing these two equations, we have the final expression, lambda is equal to h upon under root 2 meev. H is again, as I said, lambda is a wavelength, h is a Planck constant, m mass of electron, E is a charge of electron, V is a potential. So just by the constant, we get the simple equation, lambda is equal to under root 1.5 nanometer per voltage. So by knowing the actual voltage, we can find out the wavelength. So by applying the particular amount of voltage, you can have the different wavelength. So as you, it's a reciprocal equation, you can say. As you increase the voltage, you have a smaller wavelength, so you can go deep inside the material. But higher resolution, higher acceleration may defect the materials, you can say. So wavelength of electron depends on accelerating voltage, which is given by this table. You can briefly say that to require the nanomaterial sizes, we should have around 10 to 15 kilo voltage. So higher acceleration gives you higher resolution, but it has some catch. Let's see. This is a general picture where an electron gun is there, which actually made up of cathode, which electrons which emits the electrons, passes through anode, and there are some magnetic coils around that, which is called magnetic lenses, which actually used to focus the electrons to a particular segment. Then there are different phenomena occurs over here. So this is just a block diagram. Another block diagram. These are two types of, as I said, there are two types of microscope, transmission and scanning electron microscope. This is modern semiconductor, modern type of scanning electron microscope, where you have a motorized stage where you can particularly focus on particular place where you want to desired interaction of electrons with the sample. So this all must be in a column. As I said, why it is called, it is mounted vertically. So vertically mounted scanning electron microscope is easily generate the high potential, and it requires some amount of vacuum. So this is generally nowadays available kind of scanning electron microscopes. I don't go deep inside these things. So this is more detailed look inside the electron microscope. So when these electrons interact with the specimen, there are three phenomena which is occurring over here. So I'm discussing that things. But the first is, what is the advantages of SEM over M? By using this M, you can have a three-dimensional sample representation. You can have a high resolution and have a high magnification. So by combination of this high magnification, large depth, and greater resolution, you can have a compositional and crystallographic information. So instead of using, this is just for this. What are the main applications of this scanning electron microscope? So main applications of scanning electron microscope is a topography, where you can identify the surface features of the object, their texture, hardness, reflectivity, diffraction conditions, etc. you can identify. So this is topography, which is generally used to identify the surface features. Morphology. Morphology is important thing where you have a semiconducting materials. So it defines the shape and size of particles, and what constituent particles make up of object. Make up the object. That is the important thing. So strength, defects in ICs and chips are generally studied by using the morphology. Again, I said compositional, the elements and compounds present inside the material, and what are the relative compositions. So you can also find out the melting point, reflectivity, hardness, etc. by using these compositions. And crystallographic information, like which kind of crystal is present, which kind of crystal structures and phase groups and other important things regarding the crystallographic information you can have by using this main applications. We have the different source of electrons in this. The first source of electrons is a tungsten, which is widely used. The second is called LAB6, which is also used to get the higher resolution. because it emits the large number of electrons, and it also having the lower energy. So you can say energy efficient electron gun properties are there. Then there are different kind of field emission guns are available, cold and thermionic, which is also used to get the different particle size and state interaction with the surfaces. But they different. All these things requires a vacuum. So why we need a vacuum? So vacuum in a SEM, vacuum is used in a sample so that the electrons which are scattered from the gas molecules should not interact with the other elements present inside the chamber. If the electrons interact with the other than the what we want to study, then it has a no use, you can say. So if you make the chamber vacuum, then the gas molecules lead to reduction of beam intensity, and it will enhance the beam intensity, and it will enhance the stability of the material. So you can study material for a longer duration, you can say. So if other gas molecules will be present, then it will be contaminated, there will be contrast, there will be obscure details in the image. So it's a must need in this scanning electron microscope. Generally, it is inbuilt nowadays, so you don't have to go for another things. So when you purchase a SEM, the diffusion and rotary pumps are attached with that. So you need to just switch on. Vacuum is already created around 10 to power minus 5 or minus 7 volt, required on what kind of voltage you are using. As I said, basic principle of this is the electrons, where you are using the electrons. When it interacts with the surface, there are three possibilities. So when electron interacts with the surfaces, there will be transmission, there will be Auger electrons, there will be scattering of electrons called scattering electrons, there will be backscattered electrons. So let's briefly discuss what are the Auger electrons, backscattered, and secondary electrons. So the Auger electron is a physical phenomena in which the filling of an inner shell vacancy of atom is accomplished by emission of electrons from the same object. So when the core electron is removed and leaving a vacancy, an electron from higher energy may fall into the vacancy. So that may result some energy, although most of this energy is released in the form of photons. So this energy can be transmitted to another electrons, so which is also ejected from the electrons. So the second electron, which is ejected due to the phonons of energy which is released from first electron, is called Auger electron. Auger electron spectroscopy, Auger electron scanning microscopy is important. Secondary electrons, it is generated by ionization products. They are called secondary because they are generated by other radiations. This radiation may be in the form of ions, electrons, photons with sufficiently high energy. And it will be, again, exceeds the ionization potential, as obvious. In a backscatter, where beam of electrons are reflected from the sample by elastic scattering. So since they have much higher energy, that of the second energy, and emerges deep inside the location. So when you have a deeper inside, when you want to have a deeper inside the material, you should use the backscattered spectroscopy. This is a secondary and secondary electron spectroscopy, as I discussed earlier. I may skip this. These are the semiconductor detector for backscattered electrons. semiconductor detectors by using backscatter, you can see the compositional image differences. This is without, and this is with backscattered spectroscopy. So you have a larger information of composition and topography. So I have summarized all this in a simple slide over here. So when electron beam and specimen interactions occurs, if you have the electrons, you have primarily backscatter electrons. By backscatter electrons, you can have the atomic number and topographical information. Like you can say which element is present, I can say. Cathode luminance, by luminances, by you can identify the electrical information. The secondary electrons, you can have the topographical information. Again, the same as a backscatter, but as I said, secondary electrons go much deep inside the material, so you have the in-depth analysis of the material. Auger electrons, this is nowadays important. It shows the surface sensitivity. Again, it also provides you the compositional information on the surfaces. When electron interact with the sample, there may be some X-rays also emitted out. So by using the X-rays, you can know the depth of the sample, or you can say the thickness or compositional things of the compositional information of the sample is available. Again, you have the electrical information also, like if you provide this current or you provide the voltage of that, you can identify this material which is semiconductor, insulator, or semi-metal, and by knowing this interaction of electrons with the sample, you can have this kind of information. So this is called the characterization. As we discussed, these are the EDS, electron scattered and secondary detectors are there. These are the sample stages mounted inside this SEM. I have given you the interaction volume over here. So different surface specimen produces different kind of images, and this requires different voltages. So if I put 10 kilovolt, if I put 20, if I put 20 kilo electron volt, if I put 30 kilo electron volt, if I put 30 kilo electron volt, the interaction volume may be different. So interaction volume depends on accelerating voltage. It also depends on surface of specimen. You have a different specimen, you should use the different interaction acceleration voltage, and you have a different interaction volume. This is I just skip this part because time is very short. So these are the escape volumes of various signals, you can say. Depth of secondary is much more compared to the backscattered and Auger electrons, which is around 10 nanometers. So secondary electron scattering or secondary electrons with the SEM is nowadays very useful, you can say. I also skip this. So what if we increase the voltage? So if you increase the voltage, the effect increase, obviously, as I discussed, lambda is increased. So you have a higher resolution, and your penetration will be more. So interaction with the specimen will be more. So specimen charging increases. In some cases, like in insulator, the specimen charging is important. So you can identify how much, how the property of, or what are the conductivity and resistivity of this material. Specimen damage is also increases. If you increase a higher amount of voltage, your specimen may be damaged, and there are some contrast issues. So you need to identify what kind of interaction of electrons with this specimen requires. I have given some brief of what are the magnification in the image formation occurs in a SEM. So beam is scanned over the specimen in a raster fashion, which is which is length of the scan, and length of the scan of the specimen on the CRT. When you take the ratio of that, you have the magnification. So I have given you the example over here. This is 10 micron size, and this is 1.2 micron meter size. So higher magnification may be available by using the different kind of scanning scanning and CRT combinations. So an example of this resolution is given over here, where we have given the spherical late particles. You can see there are 4 images. By looking at, you can identify that resolution for particular size is increases. I have taken this at the different oscillating voltages. Topographical image, as I said, surface information. So defect in semiconductor devices, you can identify. You can orientations of the plane inside the crystal. So there are different applications of this. I have a large number of images over here, so we can go quickly one by one. So this is micrograph of terbium doped with the gallium arsenide. This first one was taken without doping, and next one was taken with the doping. So you can just identify the dislocation concentration from second images. So a specimen here, by using the scanning electron microscope, we can identify the fracture surfaces, electronic devices, fibers, coating, particles, etc. I give you the brief for where this scanning electron microscopes are actually applied nowadays. These are the surfaces, as I said. These are the nano synthesized materials, viruses, and all the things. So let's discuss some important applications nowadays which are used in different fields. As a part of physics, I should say that physics and applied sciences are having the vast applications, starting from structure to defect identification inside the material. Structure is nothing but as I said, you can say face-centered cubic crystal and to all the crystal structures. In situ characterization, when you're preparing some materials, let me give you some examples. A material which is not available in abundance, it is not available on the earth, you can say. By combination of 2 elements, we can prepare that material. Let's talk about one carbide material. It is called platinum carbide. Now, generally, this platinum carbide does not available in ambient conditions. That is, it is not available at a room condition. But somehow, in a lab, you can prepare it. By high temperature, high pressure, you can prepare this material. And after preparation, what you need to do is you need to identify the structure. So in that case, this SAM is used. So it is also reported. Material qualification, important thing nowadays. So how much quality, how much strength, how much ductility, or how much important this material is, you can identify. Dynamic material experiments are also done by using this SAM. There are different processes like electron beam induced deposition, etching techniques. There are different kind of depositions are there inside the material. I give you example of that later on. So this is also used nowadays. Mining is also there. In mining, in nanostructures, it is also there. Nowadays, as I said, nanotechnology is a vast field. You can use it abundantly. This SAM is having the highest application nowadays in nanotechnology. So some pictures of taken by Sam. This is NaCl crystal at different resolution, you can say, from first micron size to 200 nanometer size. So you can clearly identify the structure of the material. This is platinum carbide tip. This platinum carbide tip is used as a filament tip also. So some has taken the SEM picture. You can clearly identify the atoms placed at different points. The next is ferrous crystals, where scanning electron microscope of ferrous crystal is here. You can clearly identify the size of the large single crystals. The calcium carbide structures, આપણે જે ખાવાનો સોડા કહીએ એને, this is the formation of that. Very good picture of particular stacks are there. Nowadays, this is also going on largely, where you can dope some materials with the different materials. Here, nickel photonic crystals, self-embedded in polystyrene template are there. This is of 5 micron meter size. The same with the graphene sheet, where you can identify the actual bonds between the atoms, and the size of that bonds also you can identify, and you can have the size of atoms. Same gallium arsenide photonic structures are there. Clearly you can say that photon is captured inside the hole. This is also one of my friend has done these things, uric acid crystal, which is present in our body. So these protein crystals are having the needle size, and you can identify the amount of uric crystals in a particular sample. Large applications, as I said, is in nanosciences. So we have the nanotubes, carbon nanotubes. This is a 10 micron meter nanotube, which is taken in a cross-sectional view. In a rectangular pore, you can say the tunnel inside visible inside the wall. So this is amazing, you can say. Up to 1 nanometer size is also reported for this. This is important nowadays, solar cell. So what we are using that solar panels nowadays have made up of different techniques, like spiraling or pyriding or any other processes. So when they prepare it, they prepare a small thin films. They dope with some other materials. CZTS nowadays are very attractive because it has a higher efficiency compared to the other solar panels. So clearly you can identify the structures and its stacking. Same thing, by different annealing techniques, you can say that different combination of solar photo solar cells are available. In a raster fashion, some etching, some may vary the etching time, some may varying the temperature and annealing processes. So you can have a different applications of this solar film studied by SEM. In a textile nowadays, merino wool is very important. Wools, you can say, they prepare some they include some nanoparticles inside the merino wool, and they study this for different applications. Same thing, this is important. The scanning electron microscopy image of double helix using the carbon nanotube yarns. So this is of 300 micron meter, so around used by using 10 kilo electron volt. This was studied around 2019 by Dr. Kao in Peking University. This has a vast applications in nowadays. This was studied around 2012, but recent papers also reported that it is studied vast. It is having vast applications nowadays. In other fields like forensic sciences, insurances, litigation supports, where you can analyze the gunshot residue, jewelry examination, firearm, bullet marking, handwriting analysis, banknote authenticity, and paint particle fiber analysis, etc. So I can give you an example of this. This is a bullet mark. So bullet and residue of that bullet marking on the bullet cage. So you can identify that particular bullet is fired from particular arms. So this is firearm analysis nowadays going on drastically. This has the highest application nowadays. In US, the forensic has a very large applications. So each forensic lab has a SAM. Nowadays, we are more scared by coronavirus. So I have given you a simple image. This is just reported around March. So collection of new coronavirus SARS-CoV-2. This is taken by SAM. The size of this coronavirus is around 0.125 micrometer. So it is around 125 nanometer size. This is just taken from the Nature publications. Same thing with the different color combinations. So now color combination or color SAM images are available also there. So as I said, there are different kind of biological, soil, rock sampling, medical sciences applications, and different kind of other applications are also there. In biology, identify of different diseases, viruses, and medicine, vaccines, these are also studied. In other branch, arts. So we have the monographs or some digital artwork is also identified using the SAMs. So what are the, I have given you a glimpse of advantages. What are the disadvantages? The disadvantages is the cost. It has a high cost. So particularly scanning electron microscope cost around 1.5 or 2 crores for different sample sizes. Sample preparation is one of the things. For transmission electron microscope, you need to have a thin film. And important thing is what you need to see. Some other factors are maintenance and requires a dust-proof chamber and all those things. So it has some disadvantages. But the information provided by the SAM is very useful. Some important links for the fellow students. This is a virtual lab going on at IIT Kharagpur. This virtual lab provides you the actual structure characterization. So this is just an image of this. I have connected this structural characterization of material. You have a list of experiments where you can have the all the experiments which you can perform by your own. So I can give you the first one, production of and measurement of X-rays. You can use the simulator to get the different images. This is one of the important I have encountered since so many times. Then we have, you can have this sample analysis. If you prepared some materials, you can have this analysis at different places. So first is CCART. First is you can say at RRCAT, Center for Advanced Technology at Indore. So this is also having a high resolution. It is having high resolution scanning electron microscope, having the voltage of 150 kilovolt. 150 kilovolt, I can say around 200 kilovolts. So you can imagine the magnification power of this things. We have the same scanning electron microscope in Gujarat also. There are different labs which are having, particularly in and around Ahmedabad or Vadodara, you can say, at SICART, SICART. SICART is at Vallabh Vidyanagar, and they have the unique transmission electron microscope, scanning electron microscope, and they have all the facilities of characterization. So this is the information I want to give. Lastly, you can also find out the other nanoscience instruments. And thank you.
Thank you so much, sir, for very informative session. And now I would like to request the participants, is there any question?
Sir, I have one question from my side. First of all, very nice informative session for the budding research students particularly. And I am working with the quartz material, and I have prepared this synthetic quartz crystal. It is a very tough crystal, and with the help of ball milling technique. And I achieve 87 nanometer, average nanometer, and 37 crystalline nanometers.
Okay.
And you know that the quartz is highly influenced with respect to temperature and shows the phase transformation. So my question is that, is there any technique to identify the phase transformation effect? This is the first question. And second, will it possible to correlate my applied research with theoretical research? That means, can I resolve with the help of any theoretical softwares? So one thing is that the phase transformation is the well known, but other than phase transformation, theoretically, can I define or determine?
Yeah. So this is very interesting. Particularly the scanning electron microscope which we are using right now doesn't provide you that information. But X-ray, maybe X-ray can provide you that kind of information at high pressure. Even you can use it up to, you can say very high pressure, you can identify, I can say 500 kilobar up to that pressure that you can apply, and you can identify the phase transformation. So this is the first thing. You cannot use it SEM. Particularly SEMs are used, but now this particularly in and around Gujarat, we don't have that kind of facility. You can use X-rays. This is one thing. Then second thing is for theoretical physicists, this is there is a different you can say first principle applications, when you can directly correlate your simple CIF files. And by using that CIF file, you can directly generate the stable phases by applying different phases and by doing the different phase structures, or by just simulating that things, you can identify the structure. So you can identify the phase transformation around particular pressure. That is also available. So this is one of the good research nowadays, and it has been going on since so many times. I have read number of papers of this. Like even we have done these things, as I discussed in our in this that platinum carbide. So platinum carbide was the structure which is not available at a room temperature. So it is synthesized at high temperature and high pressure. So we have predicted that this structure will be of this phase at room temperature. So theoretically, it's a possible. Practically, as I said, you need to use X-rays.
Thank you, sir.
Thank you.
Thank you so much, sir. Yes, sir. Now, is there any question from any participant? Okay, I think there is no question. So, there is no question. So, I would like to express my sincere gratitude to our today's speaker, Dr. Mitesh Joshi, sir. First of all, for accepting our invitation and for providing the very informative session for all of us. I would also like to thank all the participants and the viewers to be present for the today's webinar. And once again, I thank you so much to Dr. Mitesh Joshi, sir, for the very informative information, not for the researcher as well as our BSc and MSc students also. Thank you so much, sir.
Thank you, sir. Thank you.
Thank you.